For today's warm-up, I'd like you to use what you learned yesterday about improper integrals to rewrite this as a limit and evaluate this improper integral. So please pause the video and give students 2 to 3 minutes to do this. All right, so we know that we can't just leave the infinity there, so I'm going to call this the limit as b approaches infinity of the integral from 1 to b of x squared dx. I can now integrate, and so this is the limit as b approaches infinity. Integrating this gives me 1/3 x cubed, and that's going from 1 to b. And so the limit as b approaches infinity of 1/3 b cubed minus 1/3 times 1 cubed. As b approaches infinity, this one is infinity cubed, which is infinite, minus 1/3, that is infinity. So my answer is that this integral is divergent. My answer is not infinity, my answer is divergent. Here are the answers to last night's homework. Please pause and make sure you understand these. Okay, so what we are going to learn today are some techniques for telling whether an improper integral is going to converge or diverge without actually evaluating it. All right, so what we know is that if an improper integral is going out to infinity, anything that is going to have a prayer of converging, anything that has a chance of converging, must be decreasing to 0, the function itself. If the function itself is not decreasing to 0, for example, if I'm looking at something like this, and I'm integrating it from, let's say, 1 to infinity, this area is just going to be getting bigger and bigger and bigger. This is going to have an infinite area. However, if the function is decreasing to 0, and I integrate from 1 to infinity, as I get out to infinity, the area that I'm accumulating is getting so small that it becomes insignificant enough for us to say that we are approaching a finite area. And so anything that is going to even have a chance of converging must be decreasing to 0. Decreasing to 0 is not enough, because you saw yesterday that the integral from 1 to infinity of 1 over x dx, which is a function that's going to 0, diverges. So going to 0 is not enough, but it is required in order for us to have a prayer of converging. So for example, what you did in the warm-up, x squared is not going to 0. From 1 to infinity, it's doing that. And so the area underneath is getting bigger and bigger and bigger and bigger. 1 over x squared plus 1. As x goes to infinity, this function itself is not approaching 0, it's approaching 1. So out at the end, I'm adding something that has a horizontal asymptote at 1. It's just going to be getting bigger and bigger and bigger. So these are both going to diverge without me having to really do any math about them, because neither integrand, neither function that I'm integrating, is approaching 0 at infinity. So we now know the convergence or divergence of a few important improper integrals. In the warm-up, you saw that x squared diverges. Yesterday in class, you saw that 1 over x converges and 1 over x diverges. And 1 over x squared converges. What I'm going to teach you today are a few theorems that help us use these to test the convergence of similar integrals. First, we can generalize a set of improper integrals called p integrals, where p stands for power. The integral from some positive constant a to infinity of dx over x to the p, where p is my power, p is a number, converges if and only if p is greater than 1, diverges if and only if p is less than or equal to 1. So p bigger than 1 converges, p less than or equal to 1 diverges. This allows me to tell whether an improper integral converges just by looking at it if it fits this model, dx over x to the p. The reason for this is if the power is greater than 1, then when I integrate this, I still end up with an x in the denominator. Bringing the power up by 1 still leaves me with essentially a negative exponent, an x that's going to go in the denominator. So as I evaluate out at infinity, that infinity term is going to give me 0. If p is less than or equal to 1 and I bring p up a power, well then this x is going to move into the numerator and I'm going to end up with infinity when I evaluate at my top limit of integration. If that didn't make sense, that's okay. I'd like for it to make sense, but if it didn't, this is a rule that you can just kind of commit to memory. So actually, I'd like to look at the ones that were on the previous slide. We had the integral of x squared dx. Let's just do all of these from 1 to infinity. The starting limit doesn't matter too much. And then we had 1 to infinity of dx over x. And then we had 1 to infinity of dx over x squared. I'm going to leave this one for last. Dx over x, what is the power attached to x in the denominator? P equals 1, so this diverges. This one, the power in the denominator is 2, which is greater than 1, so this converges. My goodness, I'm sorry, guys. This, the power in the denominator, if I wrote this as dx over x to a power, that power would be negative 2. Which is less than or equal to 1, so this one diverges. All right, let's say it's not quite a p integral. Let's say it's close. We might be able to use something called the direct comparison test. The direct comparison test tells me two things. If the function that I'm integrating is bigger on the bottom, like larger in the denominator, which is making it smaller in total, than an integrand that is known to converge, then my new function converges as well. So smaller than a convergent converges. It also tells me that if a function is smaller on the bottom, so has a smaller denominator, that makes it bigger in total than a function that's known to diverge, then the new function diverges as well. So bigger than a divergent diverges. Okay, I can show you this kind of visually. Let's say I have this integrand that converges. Okay, this is a finite area. Well, if I'm looking at something that is less than that, then at every x value, this curve is going to fall under the curve. And wouldn't you say that if that top curve converges, then anything underneath it would converge as well? I can make the same argument for a divergent function. If this guy diverges, then its area underneath is infinite. It's not finite. And so wouldn't you say that anything that's bigger than that would diverge as well? Okay, so there's kind of a terrible visual proof, I'm not even going to say the word proof, of this direct comparison test. So let's use this for a few examples. With these, we first have to decide what we're going to compare it to. So I'm going to write compare to, this minus 1 is kind of insignificant out at infinity. So I'm going to compare it to the integral from 2 to infinity of dx over x. What does this do? Converge or diverge? Well, p is equal to 1. Therefore, it diverges. This has x minus 1 in the denominator. So 1 over x minus 1 is smaller on the bottom, therefore bigger in total than 1 over x on the domain that we're looking at from 2 to infinity. Where we're concerned, 1 over x minus 1 is bigger than 1 over x. So since this function is larger than a function I know to converge, I'm going to write therefore diverges by direct comparison. you need to show all of this. You need to say what you're comparing it to, what it does, show me that we're on the correct side, greater than or less than, and then give me your conclusion. For the second one, what am I going to compare to? Well, I'm going to compare to the integral from 1 to infinity of dx over x squared, because that plus 1 is going to be insignificant out at infinity. Now for this one, the power in the denominator is 2, which is bigger than 1. So I'm comparing it to something that converges. 1 over x squared plus 1 has a plus 1 in the denominator. It's bigger on the bottom, therefore smaller in total than 1 over x squared. And smaller than something that already converges is going to converge. So this converges by direct comparison. All right, I'd like you to pause the video here and try these 4, okay? It says for each improper integral, choose a known integral to compare it to, state whether that one converges or diverges and why, and decide whether you can use the direct comparison test. I'm not telling you you can do all of these. Not all of these are possible with direct comparison, but I want you to try all 3 of these. Please pause the video here, and we'll go over these in just a minute. So take maybe 3 or 4 minutes to go through these 3. Okay, for this first one, we're going to compare to the integral from 1 to infinity of dx over x cubed. For that, p is equal to 3, which is bigger than 1, so it converges. X cubed plus 4, adding that 4 in the denominator makes the denominator bigger, therefore it's smaller in total, bigger on the bottom, smaller in total, than 1 over x cubed, smaller than a convergent, converges. So therefore, this converges by direct comparison. Let me change colors. All right, this one I'm going to compare to the integral from 10 to infinity of dx over the square root of x. What is the power in the denominator here? Well, it's 1/2, which is less than or equal to 1, so this diverges. 1 over the square root of x minus 4 compared to 1 over the square root of x. Well, this has a minus 4 on the bottom. It is smaller on the bottom, therefore bigger in total than something that already diverges. Bigger than a divergent diverges, so therefore this diverges by direct comparison. Last one. I'm going to compare to the integral from 1 to infinity of dx over x. The power is 1, so this diverges. 1 over x plus 1 compared to 1 over x. Well, this is bigger on the bottom, therefore smaller in total than something that diverges. Smaller than a divergent. Might diverge, might converge. We don't know. You cannot do this third one using direct comparison. You cannot. Smaller than a divergent tells us nothing. It is inconclusive. So what do we do in this scenario? If you cannot use direct comparison, then you may be able to use something called the limit comparison test. In the limit comparison test, let's say the positive functions f and g are continuous on some interval from a, which is a constant, to infinity. If I take the limit as x approaches infinity of f of x over g of x, and I get a number, L, not 0, not infinity, but something non-zero and finite, then f and g either both converge or both diverge. They act the same way. Let me explain this in a little bit cleaner language. I take the integral that I'm given, okay, and I kind of strip it down and compare it to what it would behave like out at infinity. Okay, so if there are constants, I get rid of those. And then I take the limit as x approaches infinity of the one that I know over the one that I want, or the one that I want over the one that I know. It doesn't really matter. And as long as I get a non-zero finite number, then both of them do the same thing. If I get 0 or infinity, that means I compared it to the wrong thing, and I should go back to the drawing board. Let's do a couple examples. Here's another explanation. Pick a known function g of x, meaning basically a p integral, and take the limit of the ratio between the question and the one that you know. If you get a number, f and g do the same thing. So let's try this one. I have the integral from 2 to infinity of dx over x squared minus 1. I'm going to compare to the integral from 2 to infinity of dx over x squared. For this one, p is equal to 2, which is greater than 1, so this converges. Now, 1 over x squared minus 1 is smaller on the bottom, therefore bigger in total than 1 over x squared, so I cannot do direct comparison. You don't need to show this step necessarily unless I ask for it, but direct comparison in most cases would be easier. I'm still going to compare to dx over x squared, but I cannot do it using direct comparison. So instead I'm going to use limit comparison. I'm going to take the limit as x approaches infinity of one over the other. It doesn't matter the order in which you stack them. This is going to be 1 over x squared over 1 over x squared minus 1, the one that I know, over my question. And then I just evaluate this limit. Now I'm dividing two fractions, so I'm going to kind of, I hate saying this, but keep it, switch it, flip it. And this is going to turn into x squared minus 1 over x squared. If you're having a hard time getting from here to here, ask a friend. Now I'm dealing with a limit at infinity. I can think of this as end behavior. I have the same power, numerator and denominator, so my limit is going to be the ratio of their leading coefficients, which is just 1 over 1. The number that I get doesn't matter. What matters is that I get a number. Getting a number means they do the same thing. So since the one that I'm comparing it to converges, then the one that I want converges as well by limit comparison. Let's try another one. I have x dx over x squared minus 1. Honestly, I actually think you could do direct comparison here, but it's icky, and so we're just going to go straight to limit comparison. So I'm going to compare this to the integral from 2 to infinity. Now, guys, I have to decide what matters here. Does an x in the numerator matter as I go to infinity? You bet it does. Okay, I'm not just going to call this 1 over x squared. Anything that's infinity is going to matter. Basically, the highest power in the numerator and the denominator is what you're going to be looking for. So the highest power in the numerator is 1. This x squared is going to matter. This minus 1 is not. Even if it were minus x, it wouldn't matter. What matters is the highest order term, numerator and denominator, because out at infinity, that's what's going to dominate the behavior. So my numerator is an x, my denominator is an x squared. I'm going to compare this to dx over x. Okay. And so I'm going to use limit comparison. Oh, let's talk about what this does. The power is 1, so this diverges. Limit comparison, I'm going to take the limit as x approaches infinity of 1 over the other. Let's do 1 over x over x squared minus 1, which is the limit as x approaches infinity of 1 over x times x squared minus 1 over x, or the limit as x approaches infinity of x squared minus 1 over x squared. As I'm going to infinity, I have the same power, numerator and denominator, so my limit is the ratio of their coefficients, which is 1, One doesn't matter, but what matters is that I get a number. That means they do the same thing. So this integral diverges by limit comparison. That is my answer. Notice that these comparison tests, direct comparison and limit comparison, if I get an answer of convergent, it doesn't actually tell me what it converges to. It just tells me whether it converges or not. All right, I have these 5 homework problems for you. You can use the rest of class to work on these. You can use either direct comparison or limit comparison, provided that either one would work. You know you cannot use direct comparison in every case. There are also cases where you can't use limit comparison, okay? And you'll see some of those, I'm not sure in this homework assignment, but definitely in some practice problems that you're going to have later on, okay? All right, thank you.